in the list here, all the Greek symbols, you have capital and small letter, right? So you can see some of it we are using, like alpha, gamma, beta, delta, all this we always use, right? So if you go to my vibration class, then you start to see the zeta, eta, all this. So also kappa, right? So you can see all these symbols. So that's why omega, the symbols you use for your electrical resistance. Yeah. So it is these symbols. So for us, we use the small letter normally for angular velocity, right? So I think this one you can also learn, right? So because when you start to writing your thesis, right, your FYP report, you'll use this numbering. So if you can notice that we seldom go all the way to 50. 50 is L, 100 is C. Okay, so you can have a look or keep it for yourself. So for your reference, all this information, right? So somehow they have a common use property, right? Unless it's being specified, right? So all the symbols normally has a standard use of it. Okay, now we have 193. Yeah. Okay, so we will move to the lectures. Then only I start the recording. Okay. Okay, I turn on the recording now. Again, good morning to everyone who are here. Hopefully more and more students will join in later. So based on the last week, we stop here. So we can use the graphical way to do this acceleration calculation, accelerations. So we can also use the analytical solution method. Okay, so by looking at this 4-bar pin joint linkage, so this is the vectors formulas we have. So we have R2 plus R3. Actually, it's R2 plus R3 equal to R4 plus R1. So we move the R4 and R1 to the left-hand side. So it becomes R2 plus R3, which is this one, R2 plus the R3. Right? So it will be equal to R1 plus R4. So if you write it, then you can have R2 plus R3 minus R4 minus R1. So it will back to this position, right? So this is position vectors for this 4-bar linkage. So we have the position for link 2, link 3, link 4, and the ground link 1. So if we differentiate it with respect to time, right? So we will get this velocity for link 2, link 3, and link 4, right? Because the ground link is not moving, the D is just a fixed value. So if you differentiate with respect to time, it will become 0. That's why we don't have the the velocity for link 4 here. Then if we differentiate it again, the velocity then we'll get the acceleration. So by differentiating this, we will get two components. One is the normal, one is the tangential acceleration. So normal, tangential for link, this is link 2, link 3, and then link 4. So this one we try to rearrange it so we get these vectors for accelerations for the 4-bar linkage. So if we have a relative motions, so we can actually use this, right? As long as for example, this one is actually, we can write it as AB is equal to AA plus ABA. So in textbook, sometimes you see put the slash there, it's the same thing, right? So as long as we know AA, so we can find AB by finding the relative acceleration at point B relative to point A. Yeah. So for this one, we will still discuss a lot in the dynamic force analysis in the next topics. So AA, the acceleration at point A, will have two components here. So it's depending on whether we have alpha 2 and omega 2 both together. Just for your info only. Yeah. So in most of the case, we only have omega 2. Okay. So normally alpha 2 is 0, but it depends on the questions. If the question is giving you the alpha 2, then you have this value. Okay. So for ABA, then most of the time, even though we don't have alpha 2, but we still have both components. Okay. Most of the time. So that's why this one will always have alpha 3 and omega 3, which we can find, especially the omega 3 we find from velocity analysis. Right. So as I mentioned, if you're doing it with the graphical method, so you can use the instantaneous center to find the omega 3. Okay. So once we get the omega 3, then we can, in the graphical method, then we can easily find the AB, at least the AB tangential. Right. So now if you look at the derivation here, this is the derivation of the equations. Okay. So we are trying to find the alpha 3 and alpha 4. So by giving us the alpha 2, the link length, link angle, right? And this one link angle is the position analysis. Okay, we can solve it using the position analysis. And then this one we solve it using the velocity analysis. Okay. So then we can we can substitute into the equations here, right? Which is the initial here, right? Over here. Okay. So it just break this to the xy component. So that's why you get this xy component. Okay. Right, then he multiply the operator j and try to rearrange the equation. Again, this one I don't go into very detail because this is the derivations, right? So from this one, then we can break it to the x component and the y component, right? Xy component, and then we can solve it. Because basically what we do not know is the alpha 3, alpha 4. So we have alpha 3, alpha 4. Right? So we have two equations and two unknown. Then we can solve it. So the rest, like the omega 3, omega 4, should be found from velocity analysis. Theta 3, theta 4 from position analysis. So for example, alpha 2, the A, B, C normally is given. So A, B, C, A, B, C, D. This is the link length. Normally is given in the questions. So theta 2 and omega 2 is also given, right? In the questions, normally, this one is given value, right? So that's why we can find the alpha 3 and alpha 4 in this case. So for simplicity, if any of you just want to apply the formula straight away, so this is the formula to be applied, right? We can just apply this, right? So what you have to do is, in order to find the alpha 3 and the alpha 4, so you have to calculate this A to F, right? So if you look carefully, all this information is already there, right? So we have to calculate A, B, C, D, E, F. Then we substitute into here to calculate the alpha 3. We can also substitute into here to calculate the alpha 4, right? So it depends on you want to use the graphical one or you want to use the analytical calculations. So this is the analytical calculations, right? Okay, so now this one is just move on to find the AB, yeah. Okay, because just now we have the AB is equal to AA plus ABA, yeah? So we have a AA here, right? We have a ABA here, and then the AB here, right? So again, because we know that the accelerations have a tangential and normal component, and if you want to solve it, so one of the easiest way is to break it to the x and y component, right? That's why here he expand the acceleration vector into the x and y here, similar to ABA, right? And also the AB, okay? So that we can calculate the AAX, AAY. We can break it down. ABAX, ABAY, ABX, ABY here. So then we can use this, substitute into the formula here to solve for X component. Use this, substitute into here to solve for the Y component, right? So we will do this, don't worry. So just tell you the concept. So if you have vectors for the accelerations, okay? So basically this is a vector, okay? So then we break it into X and Y component. We can solve it separately, okay? Because this one we'll still use it on the next topics, so we'll touch on this again, right? So how about if we have 4-bar sliders, okay? So this is 4-bar slider. Because of this, we have mass on the 0.4 here. That's why we have 4-bar sliders. So giving that the L1, oh sorry, let me check. Is the diagram correct? Just a second. I just have to confirm that the diagram is the right one. Okay, so I've confirmed the diagram is the right one. Huh? So this one, if you look at the textbook, is actually the example 7-2. Okay, so given the 4-bar linkage, which has the D, right, 100 millimeter at this instant time. Because once we move, the D will start to change. So that's why we only investigate, or we only calculated at the problem at this theta 240 degrees. So means here is 40 degrees, right? So L2, which is 40 over here, and then L3 link 3 B is 120, and then the C is 80. Yeah, it's over here. So it also give us the angle theta 2 is 40 degree, omega 2 25 radian per second. So now in this case it gives us the accelerations. So then we have to use alpha 2 is 15 radian per second square. So from here we can find the alpha 3 and alpha 4. After we get alpha 3 and alpha 4, because alpha 3 is needed to find the ABA, alpha 4 is needed to find the AB. Yeah? So that's why we must find these two first, right? That's the method. So then we look at the open circuit of the linkage. So this is how it looks like, open circuit. So use the angle and angular velocity, found the same linkage position in the example 6.7. So let's look at. So if we based on the information given here, right, we will notice that because theta 3, theta 4 is not given, right? So we can find these two using the position analysis. Okay, so we can find the theta 3 and theta 4. And then you also find out, so you can see theta 3 and theta 4 is not given. Theta omega 3 and omega 4 also not given. So we can find from position analysis and velocity analysis. So if in the midterm or in the exam, I ask, normally if I ask you about the acceleration analysis, I will give you this value, right? Because for you to find this, then find this, then find acceleration, at least the question will take you almost 45 minutes to 1 hour. So to skip that two parts, so normally these two will be given. Okay, then you only solve this one. You only solve the bottom part here. Okay, so we have theta 3, theta 4 finding from position analysis. Omega 3, omega 4 is here. So you can also assume that the question you will get, it will also give you this data if you are only asked to solve the acceleration analysis. So again, to use the analytical method, right? So you have to find the A to F, right? So A is C sine theta 4, right? Just put in the value. So you find the value for A. Then B is B sine theta 3. Okay, so just plug in the value and then we get this. So same for C, D, E, and F. So all this value is already in the questions. So you just plug it in. So you have to find all this numbering here, all these numbers. Okay. So once we get these numbers, we can substitute into the formulas we have here. So alpha 3 is CD minus AF divided by AE minus BD. So if you notice that this part and this part is the same, right? So for alpha 3 is CD minus AF. For alpha 4 is CE minus BF. So then from there we will find the accelerations, angular accelerations for link 3, right? And angular acceleration for link 4. Right? Once we get this alpha 3 and alpha 4, That's why then we can start to write the ABA. Okay, AAX and AAY, we can straight away write using the information given in the questions, because what is required is only the A alpha 2 and omega 2 as well as the theta 2. Right? So same for the AAY. Right? So this is X direction, this is Y direction only. But when we do ABA, that's where we need the alpha 3. Right? That's why we must find this one first. So we will take this value and plug in here. So to find what is actually the ABAX, so also the ABAY. So again, we use the alpha 3, right, in order to find the ABAY. Right? So for AB, the acceleration at point B, right? So then we need the alpha 4, right? That's why we just now we have to find the alpha 4 first before we can solve this, right? So from here we can find that the ABX is here again, then ABY Y component is here, right? So actually, if you are using analytical method, basically you can ignore this part, right? Because we have the formulas. AB is AA plus ABA. So if you sign ABX, it will be AAX plus ABAX. So ABY will be AAY plus ABAY. You just use this. Okay? So not necessarily you sketch out this, unless we trying to solve it graphical way, right? Then you can draw. You have to draw this, right? Okay, now look at another questions. This is a continual questions from the previous position analysis and velocity analysis. So linkage again given minus 36. Wait. Alright, which is here. And then the 57 is here. So then find the alpha 4, AA and AB in the global coordinate system for the position shown. And then we have omega 2 is counterclockwise. So if you look at again this one, this is a keyword, constant. When you say constant, means your alpha 2 is 0. That's why a lot of times the questions will not give you as straight away this, but it will tell you constant angular velocity. Right? When you have constant angular velocity, your angular acceleration will be 0. So here you can say we can use the analytical method. Okay. Again, this is how we write out the AA, ABA, and AB, right? Because we have to find this, right? So again, actually the AA we can easily find it, right? So again, before we continue, this is what we find from the previous one, the velocity analysis. So we skip the, over here we didn't list out the theta 3. So the theta 3 and the theta 4 is also found from the position analysis. Okay. So that's why when we have this, we can easily find the AA. So now depend on you whether you want to use this Okay. So in this question, it show you that we can, if you don't, because that's how I say we can use this one. Huh? If you don't use this, you can actually use this one. Okay. Then you substitute all the alpha 2 is 0. Huh? And theta 2. Okay. Oh, sorry. When this is 0, then the whole thing will be 0. Huh? That's why you have omega 2, A omega 2, theta 2 here. Okay. A omega 2, theta 2. Huh? And then B is here. So alpha 3 is the one we want to find. Then theta 3. Okay. B omega 3 is 5.2. And then again theta 3. So we come to the C is 0.122. Alpha 4 is another parameter we want to find. So theta 4, just now the theta 3 and theta 4 is from position analysis. So we get this value, C omega 4 from the velocity analysis, and then theta 4 again. So we have this equation. So what are you going to do next? All right. So you try to do it. So basically, then we'll break this into the x component, y component. All right. Same as what we have here. This one. All right. So we break into x component, y component. So you group all the x component into this based on these formulas. So you break it here and here. Right? So we break all the x component into here, and then all the y component into here. Okay. Then you can solve two equations simultaneously. Right? So in order to get the answers for alpha 3 and alpha 4. Okay. So from here, you'll get the alpha 3, alpha 4. Then only you will return back to this part, okay, to get your basically your AB. AA we can already calculate it based on the information given in the question. Okay, so you can try it out, and then if you cannot do it, or you can show your steps to me, so I can try to troubleshoot, okay, the problems. So this is acceleration analysis. Okay. So we will apply this a lot in our dynamic force analysis. So that's why if we move into the dynamic force analysis, you'll see we still have to do all these calculations. Okay. So we may not we are not just calculating the AB now, right? Because we also have to use the analysis acceleration analysis method to also find the acceleration at the center of gravity of the linkage, because that accelerations will be used in our Newton's second law to calculate the force, the inertia from the system. So we'll move to the chapter 2, the dynamic force analysis. Okay. So we'll go through this. So you'll see that we are using the Newtonian method. Then we will look at this pure rotation. So this normally refer to link 2 and also the link 4. So if you have 4-bar linkage, so you will find out that link 2 and link 4 is always in the pure rotation, because the fixed point of O2 and O4 is not moving. Then force analysis of 3-bar crank slider. Okay, you will see what is the difference between the 3-bar crank slider and also sorry, and also the 4-bar sliders. Then we also look at the 4-bar. So after this, then we'll look at the shaking force and shaking torque, right? So if you notice that if the linkage is not properly balanced, right? So when they start to turn, you always have this shaking force and shaking torque, okay? That's why people say the 3-cylinders engine shake more than the 4-cylinder engine. So it's basically because of this shaking force, especially this shaking force from the engine itself. Okay, so that's why if you ever go through some video who explaining about 3-cylinders engine, this is by natural, okay, that you will have a difficulty to balance the 3-cylinders engine, right? Because of its nature. Then we can also see how can we use the energy method, right? So if you can recall Newton second law or Newton method, normally we can find information about every linkage, right? For example, the force between the linkage, so we can find from this Newton second law. But if you are using energy method, normally we will find the information which is acting onto the system. So internally, the internal information will be limited using the energy method, right? So that's why if we are using Newton methods, one of the additional thing we will find is the force on the pin joint, between the linkage, right? So for energy method, then we can straightforward way. We can have a straightforward way to find the torque, right? We call it torque 1, 2, right? Which is the torque required on the link 2, right? To turn the system, right? So just now I mentioned the shaking torque, right? So one of the way to solve the shaking torque problem is by using these flywheels, right? I'm not sure how many of you know about flywheels, okay? But especially boy, you have been using flywheels since maybe you are 2 or 3 years old, because the toy car that you can push, and then you push it to make the wheel turn, and then you release, the car will move. Actually, all those toy car has what we call it flywheels. Okay, if you want a more scientific or more other way to call this flywheel, right? So you can call it also as a kinetic energy recovery system, right? Kinetic energy recovery system. So I think this one you will see this in the previously in the F1 they use this word, right? Okay, instead of using just a flywheel, because flywheels all the while is already there in the gearbox, between the gearbox and the engines. So this is additional flywheels they put in the F1 to harvest the braking energies. So introductions here, when kinematic synthesis and analysis has been used to define all the geometry, sets of motions of a particular design task. That's why we start with the position analysis, velocity analysis, acceleration analysis first. That is called the kinetic synthesis and analysis. So it is logical and convenient to then to use the kinetostatic or inverse dynamic solution to define the force and torque in the system. So under the dynamic force analysis, we can done with several methods. One of it is the Newton law, or more specifically is the Newton second law. So that's why we have the summation of force equal to ma. So remember that this is a vector function. So that's why we can break it into the x and the y component. So we have one equation here, two equation here. And then the other one is a summation of torque equal to I alpha, right? So this is the third equation. That's why if we solve the dynamic force analysis on the linkage using the Newton law, then each link, not linkage, each link will have three equations, right? 1, 2, and 3. Yeah, so we have three equations there. Okay. So now if you look at the link 2 and link 4, basically we always look at the link 2 first, because this is our input data we have, or our input link. Okay. So consider a single link in pure rotation shown in the figure below. In any of these kinetostatics dynamics force analysis problem, the kinematic of the problem must first be fully defined, right? So this is important. We have to know all the position, the velocity, and acceleration of the system, or of this link. There is the angular accelerations of the all rotating members, linear acceleration at the center of gravity, right? That's how I mentioned, right? We are no longer just find the AP, or we normally call AA here, if this is point A. So we are not just find the AA. We have to find the acceleration at this center of gravity. Okay. So the mass of each member and the mass moment of inertia IG with respect to each member CG must also be known. So that's why we also find, that's why one of the important things I keep highlighting is the mass moment of inertia that we will be using here. Right? So in addition, there may be an external force or torque applied to the members, so we have to know, right? So for example, in this case, when you see this is the external force. Okay, you can see this force is applied at the point P here, right? So that's why I call it FP. So then we have to find this acceleration at the center of gravity. So we normally label AG 2. So the 2 is referring to the link number. So AG is the acceleration at the center of gravity. So then we have to find IG2. The alpha 2, omega 2 normally is given. So this link length and the location of the center of gravity, right? So this one we normally call it A, right? This one is the location of the center of gravity of the link 2. So if we draw the free body diagram, as you may already know, that every time we want to solve the mechanics problems, so we have to have the free body diagram. So in this case, because we have a ground link here, O2, so we also have this. So even though we are not, most of the time we are not using this, but it's a best practice that you still draw this out, right? Because actually this is just a reaction force at the ground link. Okay? So we have a F21. So now let me see whether they talk about this. Yeah, so now you will see there is a lot of F21, F12, F32, F23, and so on. So before we go further, so I just want to highlight how the books or author actually name this linkage, right? And also my advice to use is we stick with these textbooks, which is the author is by the Robert L. Norton, because if you read too many books, there is a lot of symbols have been used, right? So you may confuse. So try to restrict yourself onto the same textbook as we are using for this course, which is the Robert L. Norton. Okay. So then you can follow the symbols used better, right? Don't I know some of you may be too hardworking, so maybe don't read too many books unless you are quite clear on how different author actually label the force, right? This is my advice, right? So we can just stick with here. That's why here, if you say F21, right? So what you're referring to is the force exerted by the link 2 to link 1. Okay? That's why it's right the 2 first and then 1 at the back. Because this F is the force, this force is exerted by link 2 to link 1. Okay? So we have F21. So when we are looking at the link 1, right? But now if you move to link 2, right? Now we move to link 2, we look at this point, right? The point O2 here. So what happened? If you now stand on the link 2, you'll find that at O2, you have a force exerted by link 1 to link 2. That's why it becomes F12. So what is the relationship between the F21 and F12 is the reaction force. Okay? So that's why F21 is equal to negative F12. So it means that they have the same magnitude but just opposite direction. This is a reaction force. Right? That's why now we still stand on the link 2. Now we look at the point P here. Right? So what is the force? This is a force exerted by external force P to the link 1. So normally we will not write FP1, we just say FP. Right? If in the case that we have the maybe I think take it down. For example, if we have a link 3 connected here, right? So now if I stand on the link 2, I look at this point P, right? So I can call the force is exerted by link 3 to link 2. So I can write F32, right? So that is how the label of all these force is. So then you also give us so you also give us the R12 and the RP, yeah? So when we are here, so again, another thing you may have to be very careful is the way is this R is being measured. So if you're referring to this is the center of gravity, right? Center of gravity, yeah? R12 is measured from the center of gravity to the O2, to the center of rotation at L2. So RP is measured from the center of gravity again to the point P, which is the point where the FP is applied. Yeah? The force P is applied. Right? Because this is important when we solve the question using analytical way. So you have to write this in the proper X and Y component. So for example, now if you look at here, this is my center of gravity at CG here. My R12, if you calculate it, you'll find out that your R12 X is a negative value, negative something. R12 Y also negative something. Okay? But then your RP is a positive X and positive Y. Okay? So there is that's where when we start to solve it, you'll find out that why suddenly there is a negative come into your that is in your questions. So this is one of the reference that is used by the proposed by this author of the books. So we just follow first, because later when you get used to this, then you can set your own reference if you want, right? So then they always take care that there is any external torque and external force, right? So in this case, external torque is labeled as T12. And then again, it's the same naming. So it's the torque exerted from link 1 to link 2. Okay, so it could be a motor placed at the point 02 here. So it's the torque provided by the motor to the link 2 to rotate the link 2. So then there we have a FP. So this is how we can draw the free body diagram. So we have F12, FP, torque, right, and the center of gravity is. So now by looking at these free body diagrams, right, so we can write the equation using the Newton's second law. So we have summation of force, right? We have summation of force equal to MA. So because when we write here, we are actually referring on this point. So we will say that the FP, right, which is the force here, plus the F12, which is the force here, equal to M2 AG2, M2 AG2, right? So that's why we have to know what is the acceleration here. So M2 is a mass for link 2. Then this one later will break to the X and Y component. So for the other one, the summation of moment or summation of torque equal to I alpha, right? So we have to see what are the torque or moment in the system, right? So that's why first thing we have the T12, okay? Then by looking at this point, so you'll find out that you have force 12. It should be multiplied with the radius here, okay? The R12, right? So in order to give us the torque, and then the FP will be multiplied with the RP to get us another torque to the system. Then this will be equal to the IG alpha, right? So now if we break the force into two components, so we have a FPX, F12X, and then M2, because mass is a scalar unit, so that is why there is no X and Y, but the acceleration will have a X and Y component. So we have a AGX here. So for Y component, we have a FPY, F12Y, and then AGY here. For torque, right, the third one come to here. So T12 again is just a value refer to the center of gravity here, T12. That's why nothing had to be done. But for the R12, F12, okay, R12, F12. So now if you take the center of gravity as a reference, okay, so F12Y is here. So what he have to do? So in order to find the moment or the torque, or in this case, so that the F12Y have to multiply with the R12X. Okay, so this will give us a counterclockwise component. So this is counterclockwise component. That's why it's positive. Okay. Now we look at the F12X. The force must be multiplied with the perpendicular radius. So R12Y. Okay. That's why your R12Y multiply with F12X. What you will do, this one will give us the clockwise direction. So that's why there is a negative. Okay. Then we'll move on to the P here, RP, FP. Yeah. So again, if we have a FPX here, and the FPY here. Okay, so what will happen is your FPX multiply with your RPY. Okay, so FPX multiply with RPY, it will give us a clockwise. So that's why you have negative, and that is the value. So if I take my RPX multiply with my FPY, which is this one, this gives us the counterclockwise. This is clockwise. Okay, so that's where the negative comes into the equation because of the clockwise and counterclockwise. Okay, so he mentioned here, take the moment about central gravity. Yeah. Okay. Okay, they are all should be labeled here. Okay. Okay, we can look at one of the example here. So a section of 4-bar linkage is shown in the figure below. So we have a crank. So again, link 2, sometimes they call it link 2, they call it link, they call it A, the link length of A, or sometimes they call it crank. Right? So these are all refer to the same thing. So it gives us 250 millimeters in length and has a mass of 2 kg. So it also gives us the center of gravity is located at the middle of the link. Okay. Then we will know that the AR12 is 250 divided by 2. Okay. So the value here 10, this is 10 inches. This is 5 inches. The mass moment of inertia about the center of gravity is 0.011, and then external force 200 Newton is applied at the 0 degree at point P. So what it means here is you measure from this axis, X, 0 degree. That's why the FP will stay on this X-axis because of this 0 degree. And also given that the theta 2 is 30 degree, omega 2 is 20 radian per second. Here it gives us the alpha 2 is 15 radian per second square. And the acceleration at the center of gravity is 50 meter per second square at the 208 degrees. So again, how you measure the 208 degree? So you always draw the non-rotating coordinate system. So we have the X here, 208. So this is 208. Okay. So you measure from this X-axis at its center of gravity. Okay. So this is how it gives. When we talk about force P, then you will measure at the point P. Right. You draw again a local non-rotating coordinate system, then you measure from here. Right. So it gives positive value, you measure from this direction. Negative value, you measure from this direction. Okay. So now we look at the free body diagram. So we have a free body diagram here. Again, we maintain this. Right. As I mentioned, it's good to draw it. Okay. The ground link. So we have a reaction force. Right. F21 is equal to negative F12. Then we look at the link 2. So we have force 1, 2, which is a force exerted from link 1 to link 2, okay? And then Fp, okay? So because Fp now is 0 degree, so we can also label this is just a pure Fpx. And then we have R12, just now I mentioned R12 is stated at the middle of the link. So basically it's 250 divided by 2. That's why we get 125 millimeters. Okay. And then the RP is because now this is at the middle. So RP again, the length, or we still say RP is 250 divided by 2. So you get 125. Okay. Because now this is half. Okay. So what else we have? We need to specify the AG2, right? So that we don't miss out the calculation, right? The M2 AG2. Also the top 12, T12. Okay. So you try to put all these things into your diagram. So when you write your equation, you won't miss out them. So that's why first we draw the free body diagram. Okay. Then calculate the component. Okay. So now when we start to calculate, right? That's why then you have to be very alert. R12, as I mentioned, R12 is measured from the center of gravity here. So the angle will be measured from here all the way to there. Okay. So that's why if you know that this is 30 degree here, then this is also 30. So 30 plus 180 is where you get 210. Okay. So means if we take the upper part 180 plus the 30 degree here. So that's why the R12 is 0.125 at the angle of 210 degrees. So when we calculate it, that's why you get your R12x is negative, R12y is negative. Okay. So now the RP is again same. That's how we find 0.125 or 125 millimeters. So the angle is only 30 because it's measured from the center of gravity, so it's only 30 degrees. Okay, measure up from there, the horizontal line. We call this LNCS, local non-rotating coordinate system. So we only have 30 degrees. So you can also double check that the value you calculated is a positive value. Okay. To solve this mechanics of machine, you must have some imagination. Okay. The linkage position. Okay, then for accelerations, we can also break it into X and Y. So the angle is given 208 degrees, so you can just calculate. Okay? Or if you refer back, that's why when you sketch this, if you can sketch in the more proper way, proper scale, at least close to the actual one. So we will know that AG2, it should be both negative, X negative, Y negative. That's why when you calculate it, then you can just double check. You get the negative value. Right? And then Fp is because stay at the 0 degree. So we only have Fpx, which is 200 Newton. Fpy will be 0. So then we can plug in, right? Depending on whether you want to write your own equation using Newton's second law or not. If not, then we can just base on these three equations. Okay. So you can write in. So we here it derive again the using the Newton's second law. So it expand the three equation here. Then we substitute all the value that we calculate into the equation. So we get the Fpx 200, F12x is something we want to find. Okay, it's what we don't know. 2 this is a mass M2, and then this is AG X. So we get this one, we multiply it, we get negative 88.3. So FPY is 0, F12Y is what we want to find. So M2 is 2, and then this is AGY. So 2 times the AGY, we get this minus 46.94. Then we can go down to the top. So we have T12. Okay. Yeah. So we have T12 here. So this should be the, if we check it back, that should be the R12X, F12Y, and then R12Y, F12X. So then this is the RPY, RPX, FPY, RPY, FPX, right? So we get this IG, IG2 is 0.011 multiplied with the alpha, 15 radian per second square, which is over here, even. So we have these three equations, and how many are unknown? So if you look back, we have unknown F12X, F12Y, and T12. So 3 unknown, 3 equations. So we can solve it simultaneously, right? So we just rewrite. So we will find out the F12 is negative 288.3. F12Y is 46.96 Newton, right? By substituting these two values into the top, so we will try to complete the top equations. So we will find out the top is 292 Newton. Sorry, this is, I circled the wrong thing. So the top we will get is 44.34 Newton meters. Okay. So since we have F12X and F12Y, we can find its final value. Okay. So the F12 is just the square root of F12X square plus F12Y square. So we get this 202 Newton. So we also have to find its angle. So that's why when you have this, it's also good that you draw out, you sketch out. You don't have to draw the actual scale diagram. You can actually sketch out. So we know that the F12X is negative, so it will be here. F12Y is negative, so it will be there. So the tangent, if we take tangent F12Y divided by F12X, so that is the angle we are trying to find, beta. Okay. So it should be inverse tangent. So we get the beta here. Okay. So the 9.29 that we calculated is not the actual angle that we measure from the coordinate system. It's measured from this. Okay. That's why I will recommend when we write the answer F12 is 292 Newton. Okay. So if you still maintain the 9.25, then normally we will draw like this, 9.25. So it means that I measure from this horizontal line to this, or else we can write F12 is 292 Newton at the angle of, so you have to plus your 180, yeah? So it's 189.25. So this is, then you can write it this way. So either write like this with the indication here where is the angle. Okay. So if not, then you write the general angle which refer to the coordinate system, that it should be 189.25. Okay. So this is how we calculate the force and the torque. So when we say F12, so what it means here is if you put a force sensor at the pin or at the O2, so you put a force sensor here. This is at this position at the theta of 30 degree. So this is the force 292 Newton is experienced at the pin. Okay. So and then also the torque that will experience at this O2 is at 44.34. Okay. So if you are hardworking enough, you can just simply change. You change this. You change this theta 2, for example, maybe to 40 degrees. Okay? But remember, when you change theta 2 to 40 degrees, then your theta 3 will be different, theta 4 different, alpha, omega 3 different, omega 4 different, alpha 3 different, alpha 4 different. Okay? So you have to recalculate everything. Okay? These two can still maintain. Okay? So all this will be changed, and then you'll find out that the value, these two values will be different. That is also why we will have a shaking force. Right? When these keep changing, then it gives us a shaking force. When these keep changing, it will give us the shaking torque on the system. Okay, so this is what happening. Okay, then we will recap. Actually, this is just to recap what we discussed just now. So they are defined. These are defined with respect to the local coordinate system at the central of gravity of the members. Need to resolve in x and y component. There will have to be a source torque available on the link to drive it. Right? Source torque. So that they kinematically define the acceleration. Right? So the source torque is the torque delivered from the ground to the driver link 2, and so is labeled as T12. And the other two unknown are the force component at the pin joint. So we have F12X and F12Y. Okay? So that's why in these questions, we will have two unknown here, F12X, F12Y, T12. So that's why we have three unknowns. Two at here, one at here. So three unknowns. From here, we can have three equations because your summation of force will have X, MAX. Summation of force at Y, MAY. Right? And then summation of torque equal to I alpha. So it's three equations. So these are the three equations just now we already touched on. So depend on how you want to solve it, because when we have more and more linkage, so we can actually choose to solve the problem using the matrix. Because one, you can form it in matrix, you can easily put it into the those mathematic solver program, right? For example, MATLAB, okay, and so on. So that's why we can put the three equations into the matrix format. Okay. So just label the three unknown here. This is an unknown, right? And this is all the linkage information, right? So what you mean? Then what are the force and the inertia that we have? So for example, this is M2 AGX, FPX, M2 AGY, FPY. So this is IG alpha, and all the the known value, right? This is a known information, okay? So if you look at the definition, matrix A is all the geometric information. Matrix C is all the dynamic information, okay? And matrix B is all the unknown. So the same question is given here, right? Just write it in a different way. So again, it gives us all this exactly same as the question that we discussed just now. So this is the free body diagram, okay? So same thing we do, solve for x and y component. AG also break into x and y component. FP also break into x and y component. That's why there is a lot of work you have to do to break it to x and y. So if you understand the method of solving this dynamic force analysis here, actually the most difficult part is to make sure all these x and y component that you calculated is the right one, and you substitute into the right place. Okay, so the question on this topic is not difficult. It's actually time consuming. Right? This is my opinion on this topic. The question is not difficult. It's actually very time consuming. So you have to do it fast, right, for this question. So after we do everything, we can substitute into this matrix. So we solve it in matrix form. So up to you if you did buy the textbook. So there is a program provided called matrix. So you can just plug in all this value into the program. So it will calculate for you, right? But for sure, for your midterm and final assessment, then you must calculate manually, okay? Solve the 3 equations simultaneously. It is not difficult because if you look at that, the first equation can solve by itself. Second equation can solve by itself. So once you get the f12x, f12y, you just submit onto the third equation, then you will find the t12, right? You cannot say it's very difficult to solve because we can solve one by one, right? Okay, so that is just a pure link, okay? Pure rotation link. So now we move on. Okay, we still have time. Okay? So we move on to 3-bar crank. Right? So I have to show you what is a 3-bar crank slider. So when there is more than one link in the assembly, the solution simply required 3 equations, okay, to be written for each link. So what it means here, if you have one moving link, then you have 3 equations. You have 2 moving links, then you have 6 equations. That's why when you have 3 moving links, 3 times 3, you will get 9 equations. So that's why for this, for your midterm and exam, the maximum we will stay is at the 4-bar slider, 4-bar linkage, sorry, 4-bar linkage. So you will only see 9 equations. That is the maximum. Okay. So what you have to do is you have to solve all these equations simultaneously. So 3-bar crank slide linkage, okay, is here. Okay. So again, the ground link is link 1. Okay. The one who normally attached to this O2 is called link 2. Okay. Then the link connected to link 2 will be link 3. And then there is a sliding point, right? Sliding pin here. Okay? It will slide along this direction. Right? So if we seen the diagram previously, the 4-bar slider, normally there is a mass here, M4. So in this case, there is no M4. That's why it becomes 3-bar only. So we have ground, crank, and this normally we call it coupler, right, or link 3 here. So we only have 3-bar. That's why this is called 3-bar with this slide pin. Okay, so this is 3-bar slide linkage. That's why there is no link because it's only replaced by pin movement. Okay. So in this case, we will find out that only link 2 and link 3 are moving. So you should actually expect 6 equations, right? Because 3 for each link and also 6 unknown. Right? Link 1 again is ground, so that's why we will not do any calculation there. Okay, so one by one we look at. Again, we must construct the free body diagram. So look at first one, look at this. This is the ground link. Or we call it link 1. So link 1, say similarly, we have the F21, the force from the link 2 exerted to the link 1. So F21. So it's just a reaction force from the F12. So that's why F21 is equal to negative F12. Then the other point here is the pin here, the sliding pin. So we have F31, okay? Means the force exerted from link 3 to link 1. Right? So it's a reaction from F13. Yeah? So that's why F31 is equal to negative F13. Right? So there is link 1. Then we move to link 2. Okay, so this is link 2. So that's why if you look at the point O2 here, we have F12, the force exerted from link 1 to link 2. And then the center of gravity, CG2. And then we have F32, because at this point, you will experience a force exerted from link 3 to link 2. So we call it F32, right? The force exerted from link 3 to link 2. So we get F32. That's why the distance that we measure from the center of gravity to this point here, we will call it R32. So the 32 is just follow, right? We follow the 32 there. So we call it R32. So this one, again, will follow the force here. So we call it R12. Okay? So remember, if there is any torque, we have to put in, or if there is any external force. In this case, there is no external force. So then there is what we have for all the forces. So we also try to label the acceleration just to minimize the mistake that we will do. I forgot to put the MA. So just put it there. Okay, AG2. Then free body diagram will move on to the link 3. Okay, over here. So again, this point is actually here, which is connected to the point at the below here. So now we write it as a F23, because the force is exerted from link 2 to link 3. So then it will be opposite direction of F32. Then that is our center of gravity with a measured distance R23. Right? So again, the 23 is follow the force. So we call it R23 is measured from here. So you have to see that the direction is facing there. Then the other point here up there is the pin, the sliding pin. So we call it F13 because this pin will experience a force exerted from link 1 to link 3. So F13. So it's opposite of F31. And then the corresponding R, the radius, is measured from center of gravity all the way up. Okay, so I draw the arrow bigger. So the R, we also call it R13, just follow the force. Then in this case, we check, is there any T3 In this case, T3 is 0. But then there is the FP. So we have to know where the location of FP by specifying the RP. So again, the RP is also measured from center of gravity of the link tree. And we have the FP, okay, over here. So try to be clear on how we draw this free body diagram, because later it's easy for us to write, substitute the value also. We will skip this one first, this page and this page, because we'll move to how we do the calculation. Okay. So we'll jump to here. So we have just now the figure we have. So it's 3 separate link, the link 1, link 2, and link 3. And also we draw the free body diagram. So a kinematic analysis must have been done in advance of this dynamic force analysis. So again, he mentioned there. For each moving link is angular acceleration and is linear acceleration of central of gravity as to find. For the kinematic, the analysis only the link length from pin to pin were required. So central of gravity, IG and CG are needed for dynamic analysis. So initially, CG for each link is defined by a position vector rooted at one pin joint, whose angle is measured with respect to the line center. So again, this one we have to understand. So maybe we go back to the diagram here. What it means? It means that this, the center of gravity, normally is measured with this R23. It will give you this R23 in the questions. And then you will see that there is an axis of this X prime and Y prime. Okay, so another new name will be there. This is called local rotating coordinate system. Okay. So what it means here is this axis is rotate by following the link. Right? Means that when the link rotate, this axis will follow. Right? So the X prime is always fall on the link length. Right? So for example, link 2, where is the link length? So this is the link length. Okay? So your LRCS is here. So we have X prime here, Y prime here. Okay? So your center of gravity will be the position of your center of gravity will be given as R12 with the angle here, measured from this LRCS. Same as here, the center of gravity for link 3 will be given with the R23 and its angle here, measured from X prime. Right? Because then this information will be consistent wherever it rotates. Right? That's why you use this LRCS. Right? Maybe don't ask me why so many things. We are following the books. Right? We try to use this. Because this reference point is will give us a consistent information. Right? So that's why we have a LRCS. Right? For this center of gravity, specifically for center of gravity, and also specifically for the center of gravity only. Right? So we call it LRCS, local rotating coordinate system. So we will need to define the link dynamic parameter and force location with respect to a local non-rotating coordinate system. Okay. So for the AG2, if we use velocity in the energy method, so we will base on this local non-rotating coordinate system. right? So the kinematics and applied force data must be available for all positions of the linkage for which a force analysis is desired. In the following discussion and example, only one linkage positions will be addressed, right? So this is what I mentioned. We only freeze the linkage at a specific moment. So then we see how it actually works, right? So link 2 in figure 11.2b show force acting on it at each pin joint. Yeah? So we have F12 and F32, right? So again, he mentioned here, F12 is a force exerted by link 1 onto the link 2. So F32 is a force exerted from link 3 onto link 2. So that's why then the this F12 and F32 will have equal but opposite direction force. So means that the F12 will have negative F21, F32 will have negative F23. Okay. When we now look at the link 3, we maintain the same convention as shown. Then we have F23, which is over here, right? Which is actually opposite of F32. So the naming conventions used for the position vector RAP, which locate at the pin joint with respect to the central gravity. Right? So we refer to the central gravity. Right? So the A is the first subscript is called the adjoining link to which the position vectors point, and then the second subscript P, okay, referring to this, is the parent link to which the position vector belong to. Right, so this is their the official definition from the textbook. So any external force acting on the link are located in a similar fashion with the position vector. So equation 2.1 are now written for each link. Right? So for link 2, this one we just draw it instead of FPX. Now we call it F32X. Right? Instead of FPY, now because we have link 3 there, so we call it F32Y. Right? Similar to here. Right? And just now we have RPX, FPY. So now we have R32X, R32Y. And then this one will be R32Y, F32X. Right? So this is exactly same as just now the pure rotation link. Hey, sorry, I put all the way to the end. Okay, then we look at the link 3, we have F23, yeah? So F23 is negative F32, okay? Right, so in order to reduce the unknown, so we will substitute this relation into our three equations that we create from the link 3, yeah, right? So T12 is actually the source torque, right? If we come back to here, if you mention the T12 here, so you only apply to this link 2. That's why this one, then there is no torque unless it gives you another T3 like that, right? So then only you have the torque at the link 3, okay? So that's why the link 3 in this case, it didn't specify, so there is no externally applied torque, but it do have the FP, yeah? So that's why when we write the equation, so we have F13x, which is at the pin. F, by right, when we write it is F23x, right? So because we substitute this one, then we get the negative, okay? So if you look carefully, original one, if we base on free body diagram, we should have written F23x, okay? Because we substitute this, it becomes negative F32x, okay? Then we have FPX and then M3AG3, yeah? So similarly, we have F13y. Again, this, if you look at the free body diagram, we should have been written F23y, okay? But with this relation, we will write it negative F32y, okay? So there is a negative because of the substitution here, okay? Then we have FPY and then M3AG3y. So again, this one, you can look from the diagram, the free body diagram here. Okay, so if you have the second, so we can write it R13x, R13x, and also the F13y. Okay, so this one will give us the counterclockwise. Okay, this one R13y F13x, okay, will give us a clockwise. That's why it's a negative. And then R23x F32y. Okay, so this one is a bit confused because if we base on the free body diagram, your writing or your equation should look like R23y, F23x minus R23x F23y. So by substituting the relation here, that's why it becomes negative R. Just a second, we look at the diagram by itself. This is not right. If you look at the diagram, we will get this. R23x. Hey, what am I writing? F23y. R23y, F23x. So because of changing this, so we will get negative we'll get negative R23x F32y. Okay, and then this one will become positive because the negative here, R23y F32y. Okay, So what he did here is he moved the negative outside. Okay, so that's why we'll get R23X F32Y minus R23Y F32X. Okay, so this one is what he written here. Okay, so I'll go to the same thing, the RPX FPY minus RPY FPX. So then IG3 alpha 3. So we have the sixth equation. Okay, 3 from here, and then 3 from here. So now, because the F13, okay, if you look at it, we have 7 unknown in the equation. F12X, F12Y, F32X, F32Y, F13X, F13Y. This is number 7, T12. Okay. So we only have 6 equations, but 7 unknown, so we cannot solve. That's why we have to find some way to solve it. So for the pin joint, okay, we can create a relation using the friction force. Okay, so we have friction force is equal to mu n, and the friction force is actually oppose the motion. So we can write the F13Y is equal to mu F13X. Okay, so I hope you still have an idea. When we have a box, we have the mg, so we have a normal force which is same as the mg, and then if the motion is here, our friction force will be here, so friction force will be mu n. Okay, so if we take this as a x, okay, and this is the y, so that's why my force at the y, my force at the x is equal to the mu force at the y direction. Right? So that is where we, hey, am I right? Oh, because, sorry, because the diagram we have is turned the other side. The x is here, okay, which is opposite from what I'm drawing now. Maybe I redraw it. So mean that, assuming that if I have a normal force here, then motion is there, or motion is coming down. So my Fy is here, right? So my Fy is mu n. So that's why it's the Fx. Okay. So that's where we get this, right? Because with this, then we can reduce, right? We can cut down the F13Y, right? So we substitute in the equation. That's why this part and this part, we have cut down the F13Y, right? So we left it with F13X. So we have 6 equations, 6 unknown. Okay, so if you put it into the matrix, right, you can learn how to transfer this. Or do you guys want me to show you how to transfer from this 6 equation to this matrix? Okay, so what you do is you list down this unknown. Okay, So normally we follow the sequence, F1 to X, F1 to Y, F3 to X, F3 to Y, F1 3X, and T1 2. So we follow the sequence of the link. So we from link 2 setter, then link 3, then top, right? So then you can based on your formulas, because we only have F1 to X, F3 to X, and the M2 AG2X. So that's why this is one of the F1 to X, one of the F3 to X, and then it will equal to M2 AG2. Yeah, so it's the same thing. So this is for the top equation. On the link 2, this is the top equations. On the link 3, okay? So again, if you have the program from the textbooks, so you can do a fast way. But if not, again, you can solve it manually, yeah, okay? Because all this information is known. This is a known information. So we just have to find here. So you look at here, this equation, we can straight away find what is the, we can find these two relations. Okay? From this equation, we can find these two equations, the relation of these two. And then further down on here and here. So we can solve it simultaneously. Okay? The matrix or the equation. Okay, I think I will stop here. Now is okay. Okay, so I think I will stop here for today. I believe it's more than enough for you to digest. Any questions you want to ask? May I know why my attendance list is more than the people I have in the class? Or maybe some is double click, double submit. So now we come back. I come back to the question that some of your friends asked in the chat. So someone asked midterm cover actually up to these topics, the dynamic force analysis. Okay, so we still have time to cover it. Okay, so yes, this is and then he asked whether this whatever I discuss here is important. Yes, this is the key of these topics to calculate the reaction force on the pin, to calculate the torque, right, on the link 2, right? So this is what we are trying to find. Okay, so there is only the question. The other one is someone is looking for assignment group. So anyone haven't find the assignment group? So there is one offer, right? So you can call him and join the groups. So any more questions so far? Maybe on the assignment, because the topic in the assignment, I do ask some topic which is will not be covered even until the date of submission. So there is required for you to read the lecture slide first. So you can always ask me questions. If you read, you don't understand, you can ask me first. Okay. So I will then later only cover the topics, right? Because for me, undergrad degree, you should be trained to have a self-learning capability, right? So I always explain to my advisee or those students who come to see me. So the self-learning capability is something that differentiate you from, for example, if you really want to break the ability of different degree holder. So bachelor degree is the self-learning capability is one of your additional skill compared to a diploma or certificate students. That's why we give you information that you can read, then you have to self-digest, right? Because in reality, when you graduated, you start working, all the tasks assigned to you is not identical to the sample problem you can find on the books. The books can only give you a general idea, right? So you must find your own solution. Right? That is part of the training, right? So if you don't understand, then you can ask. Similar to when you are working, your boss gives you a task. I will tell you most probably the task will not be identical to what you learn in your textbooks. But then you can ask your seniors, you can ask your boss how to solve it. Right? But then you must show me your effort of finding the solution. Then I will discuss with you. Right? Your question cannot come to me and say, sir, how to do. Right? You must tell me, can I use this method and this method? Then at least I can comment. Right? That is to train you on the self-learning capability. Yeah. Right? So if no more, then I think we can end our class today. Thank you very much. And we will have a practical session later at 2 p.m. So those who are in the practical session, we can join later. So I will stop the recording and thank you very much.